Okay, now the first section was on the electromagnetic spectrum and C equals F lambda, and we need to relate that to, or how do we relate that to atomic structure. Now here we have what we think of as a picture of an atom, a very simple picture of an atom. For example, a hydrogen atom. Now hydrogen is 1 H, so 1 proton and 1 electron, the simplest element we can look at. Now if we draw a hydrogen atom, we would normally draw 1 proton and 1 orbiting electron around the outside in an area defined by this energy level, which is energy level 1, 2, 3, 4. Now you notice as you go further away from the atom, the energy levels get closer together and reach this kind of continuum. When the electron can no longer be held, it's ejected from the atom, and that is your ionization energy. Now how do we know that these energy levels here exist? Well, if we put energy in to the atom, we can then promote that electron to a higher energy level. So if we put energy in the form of light, which if you remember, visible light is a continuous spectrum, and we measure what comes out, that would be called an absorption spectrum, because it tells me what energy is absorbed to promote that electron to the next energy level, or energy level 3, or energy level 4, or in fact put enough energy in to get its ionization energy. Now instead of seeing, remember when we're putting in the complete spectrum, red, orange, yellow, green, blue, indigo, violet, as a complete spectrum with no gaps. Now if we shine that light in, there are going to be some gaps, because energy has been absorbed to promote that electron to a higher energy level. So we still have red, orange, yellow, green, blue, indigo and violet, but what we have now are some dark lines. Now this is where energy has been absorbed and the energy is missing. So we might have one there, one here, and one here. Now this is unique for each individual atom. Now for hydrogen it's going to be quite simple because we're only dealing with 1 electron. Now once that electron is promoted, it then has to come back down again. That there would be an emission spectrum. Now, no energy is lost between going up and coming down. We're talking about an elastic energy transfer. Now, your emission spectrum will not have the colours, will not have red, orange, yellow, green, blue, indigo, violet. What it will have, though, is lines corresponding to those lines. And this is called an emission spectrum because it's the energy emitted when an electron falls back down to a ground state. Now, in terms of this is 400 nanometers, there's 700 nanometers. I'm talking about visible light, so this is 400 nanometers to 700 nanometers. Now as a short wavelength, this is high energy, and as a longer wavelength, this is lower energy, higher and lower energy. Now these gaps correspond to specific energy transfers from this electron going up to this energy level. Now what's interesting about this is you cannot get the electron going in between. Now that relates to the quantized nature of energy, and the energy will come in packets. Now what we can do is we can relate the energy, the wavelength of light emitted to the energy of that transition. Now what we do know is that energy is proportional to frequency. As frequency goes up, the energy goes up. So gamma rays have a very high frequency, they have a very high energy. Radio waves have a very low frequency and a low energy. Now to turn this proportional sign into a direct relationship, we put a constant in. So we now say that energy equals H times F. H here is Planck's constant and is 6.63 times 10 to the minus 34 joule seconds. Energy, obviously measured in joules, and frequency is measured in per second. So joule seconds times per second gives joules, which is energy. Now we have a direct relationship between frequency and energy. Now, because we're in chemistry and we're dealing with particles, we can now turn it into per mole of photons by multiplying by Avogadro's number. So we put an LHF there. That is the missing constant, which is 6.02 times 10 to the 23 particles. So we can now turn the energy now into joules per mole. So we've now got three equations. We've got C equals F times lambda, with E equals LHF. So we can now combine these two to have E equals LHC over lambda. We can directly relate the wavelength to the energy.